In the name of God. The name of our article is Attention Transfer in Self-Regulated Networks for Recognizing Human Actions from a Still Image, and I'm gonna explain it. In recent decades, the recognition of human action in machine vision has attracted the attention of many researchers. This field aims to identify human actions from a video or image. So the input of action recognition task is image or video, and the output should be action label. There are several well-known datasets for action recognition in still images, some of which you can see in the table below. This research uses two datasets, Stanford 14 and Pascal VOC 2012. The Stanford 40 action dataset contains images of humans performing 40 actions such as blowing bubbles, brushing teeth, fishing, and gardening, and etc. There are 4,000 images in the train and 5,532 images in the test, which 180 to 300 images per action class. The Pascal VOC 2012 action dataset includes 10 action classes, 4,588 images in and 140 to 220 images per class. The size of the train and the test are respectively 2,992 and 1,596 images. Recognizing human actions from images has many applications, such as image captioning, image and video analysis, human-computer interactions, and surveillance. Action classification from videos is well established, but predicting human actions from still images is less explored. Compared to video, a still image contains only spatial information without any time signs. In addition, due to changes in perspective, background clutter, human pose and viewpoint variations, rotations, blockage, and significant within class variations, a still image is more challenging than video. The low-level features extracted from the whole image are insufficient due to challenges as mentioned earlier. As a result, most existing research relies on high-level features such as parts of the human body, poses, objects, and scene context to improve recognition performance. Transfer learning methods such as attention transfer and knowledge isolation algorithms are used to extract rich features with high information value. Here are some examples of related work. Haraf et al. Introduced an innovative transfer learning method where a model learns from the transfer of information between temporal representation of videos and still images to recognize human actions. Decordi et al. Proposed a two-phase multitasking architecture in which a step, uh, coarse-grained step picks the most pertinent fine-grained experts. These experts codified the complexities into superclasses to increase the diversity within the class. The Attend and Guide Network, AGNet, which identifies images in these semantic regions and learns how to attend each region according to its importance to classification decisions, is trained in an end-to-end framework. Based on our studies so far, the attention transfer method in the teacher-student structure in emerging self-regulated networks has not been studied enough. The main foundation of this research include the following: activation-based attention transfer, transfer learning, self-regulated networks for teacher and student networks, the last function for attention transfer into four groups, random raising for data augmentation. We can see the block diagram of the proposed method in this image. We have defined four different groups for the attention transfer loss function. When training an image model, we want the model to be able to focus on important parts of the image. One way of accomplishing this is through trainable attention mechanisms. Komodakis and et al. Provided a suitable definition of attention in convolutional neural networks using a set of spatial maps as attention. In this figure, A shows an input image and a corresponding spatial attention map of a convolutional network that shows where the network focuses in order to classify the given image. Surely, this type of map must contain valuable information about the network. The question that we pose in this paper is the following. Can we use knowledge of this type to improve the training of CNN models? And B shows a schematic representation of attention transfer. A student CNN is trained so as not only to make good predictions, but also um, have similar spatial attention maps to those of an already trained teacher CNN. Consider an activation tensor of a CNN layer with spatial dimensions H and W and C channels. The input of a mapping function based on activation F is a three-dimensional tensor and its output is a two-dimensional tensor defined based on spatial dimensions. Our assumption for defining a spatial attention mapping function is that the absolute value of the activation of a latent neuron indicates the importance of that neuron concerning a particular input. We adopt the following spatial attention map constructed by computing statistics of this absolute value across the channel dimensions. In attention transfer, we aim for the student network to achieve better performance in learning and problem solving within the guidance it receives from the teacher's attention maps. In general, one can place transfer losses across several layers. We combine the cross entropy loss of the student predictions and attention losses from four groups with coefficient beta to define the attention transfer framework loss functions. Maybe you wanna ask us why did we choose self-regulated architecture as teacher and student networks? The ResNet and its variants have achieved remarkable successes in various computer vision tasks. Despite its success in making gradient flow through building blocks, the simple shortcut connection mechanism limits the ability of re-exploring new, potentially complementary features due to the additive function. A regulator module as a memory mechanism can extract complementary features which are further fed to the ResNet. Regulator module is composed of convolutional RNNs, e.g. Convolutional LSTMs or convolutional GRUs, which are shown to be good at extracting spatiotemporal information. The reason for choosing RegNet 16 and RegNet 32 networks as a student and teacher network is under the same training conditions. These two models perform better than the efficient net models and are up to 5 times faster on GPUs. In order to deal with the lack of label data, the transfer learning technique is used to train deep networks. We use pre-trained RegNet 16 and RegNet 32 networks on ImageNet dataset and fine-tune them on the Pascal VOC 2012 and Stanford 40 action datasets. The teacher network has been trained using the training dataset as the initial phase of implementation. Then the training data are simultaneously given to the non-trainable teacher and the student network that are supposed to imitate the teacher's behavior. By comparing the attention maps of these two networks in 4 different groups and the student classification loss functions, like loss function, the total loss function has been calculated. In this slides, you can see the results obtained from our tests. What emerges from this results is that the performance of the students network when it is influenced by the teachers network is much better than when it learns alone. In this picture, the attention maps of all 4 groups are shown for the student who has been trained by the teacher. The regions of the image according to which the network makes decisions about human action in the picture have a higher activation level and are brighter areas on the attention maps, e.g. girl's hand and mouth and her toothbrush for the first image and the girl's face and bubble maker and bubbles in the second image. Therefore, the student network is well trained to pay attention to important areas in the image. And in this picture, we visualize feature maps of three networks. A shows single student, B, teacher, and C, a student training with attention transfer. In any set of feature maps, we visualize the first 8 layers of each group. Well, here we have the conclusions obtained. On Stanford 14 and Pascal VOC 2012 action data sets, the optimum configuration of our method achieves 903.17% and uh, sorry, 93.17% and 91.83% mean average precision respectively. In this paper, attention transfer framework in self-regulated networks has been introduced for action recognition in ST limits. The transfer learning strategy is employed to tackle the lack of labeled data. Regulator module in self-regulated architecture helps to extract discriminative and informative features for the student and teacher networks feature maps. Numerous experiments support the finding that having at least one activation-based attention transfer loss per group enhance a student network's performance. And thank you for your time.